Hello everybody. I'm going to be looking at the general concept and implementation of a pipelining in a NIOS II instruction subset architecture. Before explaining the fundamentals of NIOS II instruction architecture, we are going to look at the basics of a CPU. The CPU, also referred as the central processing unit, is the hardware design inside the computer system which performs based on the instructions given by a computer program. There are mainly two different types of popular processors, RISC and CISC processors. CISC stands for Complex Instruction Set Computer. As the name suggests, it has a large amount of different multi-clock complex instructions. This type of processor emphasizes on hardware more than software, and load and store instructions are incorporated and based on memory-to-memory transactions. CISC processor uses transistors for storing complex instructions. Also, they are relatively slow in comparison to RISC, but at the same time it uses less number of instructions. Against CISC architecture, RISC processors are faster. RISC processor emphasizes on software more than hardware. These days, CISC processors are rarely in use. RISC uses simpler and faster instructions that is typically of size 1, so theoretically it is fewer transistors which make a RISC processor easier and less expensive to design. All operations performed on data apply to data in registers and it changes the entire register. So basically all the operations are done on registers. The only operation that affect memory area load and store instructions that move to the memory store and move from memory that are load. There are different types of instructions in the RISC such as NIOS II. The first being ALU instruction. These kind of instructions use either registers or a single extended immediate AND register. Typically, instructions are AND, OR, ADD, SUB, etc. The second type of instruction is load and store instruction. Base register and offset are the operands for this type of instructions. The sum of both base register and offset called as the effective register, and this is being used as the memory address. At the same time, for load instructions, a second register operand works at the destinations, while store instruction, the second register operand is the source of the data that needs to be stored in the memory. The third type of instruction is branches and jumps. These are the conditional transfer of control. These instructions are specified by a limited set of comparisons among a pair of registers or between 0 and registers. In RISC architecture, the branch destination is calculated by adding a single extended offset of 16 bits in case of the NIOS II to the current program counter. In order to understand how one can implement the RISC instruction set in pipeline fashion, we should understand how it can be implemented without pipeline, and therefore we will go through the basics of multi-clock cycle CPU approach. Definitely, unpipelined implementation is not economical in comparison to the pipeline CPU structure. We will understand this with the help of an example. First, we will go through the structure of a single cycle CPU. As the name suggests, in this category of CPU, it executes all instructions in one clock cycle. In reality, each cycle requires a certain amount of time, and this means single cycle CPU spends same amount of time to execute each instruction. Basically, one cycle, no matter how complex is the instruction. In order to ensure the correct operation, the slowest instruction must be completed within one clock cycle, which means single cycle CPU operates at the speed of slowest instruction. Another aspect of the CPU is, since it has to complete all the three instructions in one clock cycle, means any element must be used only once. So duplication of such an element has to be available. This points to the fact that if same element is used more than once, there will be instruction flow, and therefore different connections have to be realized, and that this is done by a multiplexer. The figure represents the combined path including the instruction memory, data memory, the ALU, and the program counter unit, and of course the multiplier in the single cycle CPU. Now we will have a look at the multi-cycle CPU. As the name implies, the kind of CPU requires multiple cycles to execute each instruction. Of course, this means the CPU take more than one will compute more than one instruction in this case for every cycle. The advantage of such a CPU over single cycle CPU is that depends upon the complexity of the instruction. More or less number of cycles can be used. For example, load instruction needs 5 stages in comparison to 3 cycles for branch instruction. Since the complexity of the operation is increased, there must be a control unit, and this can be developed using finite state machines, whereas in the case of single cycle CPU was multiplexers. Okay. Like single cycle CPU, now in this case, since the complexity has increased, total cycle time is determined by the slowest operation unit, that is the memory. Owing to the complexity of single cycle and multi-cycle processors, pipelining is introduced. Pipelining is an implementation technique whereby multiple instructions are overlapped in execution. It takes advantage of parallelism that exists among the actions needed to execute an instruction. NIOS II architecture processor is a 5-stage pipeline structure. Each stage is responsible to complete a part of each instruction as explained in the given diagram. All these 5 stages are connected through a pipeline register. The throughput of the pipeline is determined by the consideration of a fact that how often the instruction exists. As all these stages are connected, all of them should be ready to perform at the same time. The time required to move an instruction one step down to another stage among 5 stages sequentially is known as the processor cycle. The slowest pipeline stage decides the length of the processor cycle. It is the designer's responsibility to balance the length of processor cycles of each stage. It can be calculated as the time per instruction for an unpipelined machine divided upon the number of pipeline stages. If we consider the condition that then the speed of the pipelining is same as the number of pipeline stages, so it should be 5 in case of the NIOS II processor. In reality, these stages are not balanced accurately, and pipeline does not have overhead, mainly pipeline register delay and clock skew due to the setup time of these registers. Once the clock cycle is as small as pipeline overhead, then the pipeline concept is no more useful, which means very deep pipeline may not be useful. Always consider the fact that pipeline reduces the average execution time per instruction. As we have previously learned about the architecture and uses of a single cycle and multi-cycle NIOS II processor, we kind of change much of its hardware if we keep the processor exactly as it is. Because processor actually doesn't use most of the hardware if we handle instructions one by one. Because of this large inefficiency of the use of hardware available, the concept of pipelining was introduced to take advantage of the hardware by initializing the next instruction before the previous one is complete. So how does this exactly work? We look at the instruction structure of the NIOS II processor. Each instruction in a NIOS II processor has 5 different steps. Instruction fetch. In this step, we send the program counter to memory and fetch the current instruction from the memory, as well as update the program counter to the next in sequence by adding 4 to the program counter. The second step is instruction decode. It is used for decoding the instruction and reading registers as specified in register file. Also used for possible branch instructions, doing the equality test on registers as they are read. Sign extend computing of possible branch target addresses can also be performed. Decoding can be done in parallel with reading the registers since the register specifiers at the fixed location. This is called the fixed field decoding. The next stage is execute stage. In this stage, mainly ALU operations or instruction type are performed. In terms of memory instructions, it adds base address and offset address to acquire the effective address. For register to register operations as per ALU opcode, it performs addition, subtraction as it is needed by the instruction. It also performs operations for register to immediate ALU instructions. The next stage, that is memory access, mostly loads and stores instructions. If it is a load instruction, then it reads an effective address from the memory, and in case of store instruction, it writes data to memory. The last stage is write back stage, in which it performs a register to register ALU instruction or load instruction to write the result into the register file. To check whether it comes through load instruction or from ALU when it is in case of the ALU instruction. In NIOS II instruction subset architecture, there are three types of instruction: R-type, I-type, and J-type. I-type. The defining characteristics of a I-type instruction word format is that it contains an immediate value embedded within the instruction word. The I-type instruction word contains a 6-bit opcode field, a 5-bit register field, and a 16-bit immediate data. The R-type instruction. The defining characteristic for a R-type instruction word format is that all arguments and results are specified as registers. The R-type instruction contains a 6-bit opcode field, 3 5-bit register fields, and an 11-bit opcode extension field. The next instruction type is the J-type instruction. The J-type instruction contains a 6-bit opcode field and a 26-bit immediate data field. Next, we will have a look at the pipeline data path and control of a NIOS II processor. As shown in the diagram, we have a pipeline registers in between each stage of the pipeline. These pipeline stages are named in such a way it shows connections through it from one stage to the successive stage. It is known that each operation here must be complete in one cycle. We need these pipeline registers because any operation that travels from one stage to another that needs to be stored temporarily in correspondent memory registers. Operations in each stage of the pipeline structures are shown in the diagram. Let us have a look on the operations that occur on every pipeline stage. In the instruction fetch, it fetches the new instruction from the instruction memory and updates the program counter, both in the pipeline register as well as in the program counter. In instruction decode, it fetches the register, extends 16-bit of immediate data. In the execution stage, it performs all ALU operations as well, adds offset and base register to calculate the effective address. As well, it adds immediate field to the A register. During memory cycle, it cycles the memory, writes the program counter, as well as passes the value to the write back stage if it was a load instruction. In the write back stage, it updates the register from either a loaded value or ALU output. Note the fact that first two stages are independent of the current instruction, since instruction is not decoded until it reaches the end of the instruction decode stage. The first stage activity is dependent to the execution memory stage, since it has to take account